Since the beginning of civilization, astronomers have sought to unravel the mysteries of the universe. How big is it? What shape is it? And what lies beyond? Now we are on the brink of explaining these mysteries, expanding the frontier of our cosmic understanding. These are dramatic times for astronomers. They stand at the dawn of a cosmological revolution.
This is a fascinating, really exciting time. We're in the golden age of cosmology, with the largest telescopes in the world all straining to look at the most distant objects in the universe, to map out the universe in exquisite detail.
New research is preparing the way for our next giant leap forward in our understanding of the cosmos. For the first time, we may be able to measure the size and shape of our universe. In our quest to explain the mysteries of the universe, we are making dramatic new discoveries. As astronomers strain to look deeper into space, they are pushing the limits of technology. In the perfectly dry atmosphere of the Atacama Desert in Chile, these futuristic metal boxes combine to form the biggest and most powerful optical telescope in the world, the VLT, or Very Large Telescope. But this is no mere telescope. It's a time machine. As astronomers look into space, they are traveling back in time. Light travels at an incredible 186,000 miles a second. But even at this speed, light can take billions of years to travel across the vastness of the universe. Even from our nearest neighbor, light takes just over a second to reach us. We see the moon as it looked 1.3 seconds ago. And it takes light 900 years to reach us from this star in the Orion constellation. If it exploded today, we wouldn't know about it until the 30th century. Ricardo Scarpa is an astronomer who specializes in deep space exploration.
We can use all the four telescopes together to look at the same object in the sky. So in this configuration, it would be the largest telescope in the world. The light that we see was emitted billions and billions of years ago. This means that we are looking at this object as they were in the past, in the very past. So we can see galaxies as they were when they were young. And we can indeed trace the evolution of galaxies.
The extraordinary vision of the VLT has given us a history of the universe, a family album of snapshots stretching back in time. Light from this galaxy had been traveling for 10 billion years before it hit the mirrors of the VLT. Who knows what it has grown up to look like today? But is there a limit to how far back in time we can see? Our universe was born 15 billion years ago in the Big Bang. We can never hope to see anything before this moment of birth. The Big Bang is our final frontier. Now, after centuries of stargazing, astronomers have pieced together enough evidence to visualize a journey to the edge of the known universe. When the ancients stared up at the skies, they believed the edge of the universe was just above the clouds. But the more we have explored, the more we have pushed back the horizons. We no longer believe the sun is at the center of the universe. We know that the planets are just our immediate neighbors in the vast emptiness of space. The constellations were once thought to be flat patterns of stars. In fact, they are chance alignments of stars, trillions of miles apart. We know there is a natural cycle of life in the universe. Old stars explode to form vast clouds of gas and stardust, a nebula where new stars and planets are born. We know that all the stars we can see with the naked eye are part of a great gathering of billions of stars called a galaxy. And our galaxy, the Milky Way, is just one in a small cluster of galaxies known as the local group. Beyond our local group lie billions and billions more galaxies containing trillions and trillions more stars. At the heart of every galaxy, we believe there is a giant black hole. Here, the known laws of physics break down entirely. As we travel further towards the edge of the universe and further back in time, we see strange embryonic galaxies still in the process of formation. After this, around 90 billion trillion miles away, we come to a veil of radiation. We have discovered so much, but we have reached the limit of our knowledge. This is the edge of the known universe. But if we want to explore the edge of the universe, it's no good peering through an optical telescope. Light that has traveled this far, almost since the beginning of time, has been stretched. It's no longer light. It's microwave radiation. It's called cosmic microwave background radiation and shows us the universe when it was very young, less than 500,000 years after the Big Bang. It is one of the most important astronomical discoveries ever made. It will help answer questions about the origin, shape, and structure of the universe. Astronomers are now in a race to unravel the secrets hidden in this microwave radiation. At Kennedy Space Center in Florida, it's launch day, just hours before blastoff. David Spergel is a theoretical physicist. He is watching the final preparations for the launch of a space probe called MAP. He's designed it to detect and analyze in detail the microwave background radiation.
The MAP probe will take a snapshot of what the universe looked like 500,000 years after the Big Bang.
The probe is mounted 130 feet up on the top of a NASA Delta rocket. It has been 6 years in the making and is fitted with the most sensitive instruments ever blasted into space. Once in orbit round the sun, it will pick up faint radiation that has been rippling through the universe since the dawn of time.
The analogy I think of is looking out at a pond, and you see these pebbles tossed into a pond, and those pebbles generate ripples on the pond. And by looking at the ripples, and that's what we're looking at in the microwave background, we can learn two things. We can learn both about the pebbles that were tossed onto the pond, what were the physical processes that seeded the formation of galaxies, and about the pond itself. Is it made of water? Is it made of salt water? In our case, we'll learn about the universe.
This $150 million probe is the latest and most sophisticated instrument built to study these ripples in space. While Matt waits for liftoff, astronomers are already getting an insight into the promise of the microwave background using Earth-based instruments. This is the VSA, or Very Small Array, in Tenerife, in the Canary Islands. Their first glimpse has been a revelation. Richard Saunders is using the VSA to decode this radiation.
We're being able to do something completely new now with the microwave background radiation. And that gives you a window of looking directly back at what was going on in the universe when it was very young, only 300,000 years old, compared with its present age of 15 billion years.
The background radiation was generated in the fireball produced by the Big Bang. And instruments like the VSA can give us a map of the shape and structure of the infant universe. Each bright patch represents a hot spot in the fireball, where matter was beginning to clump together. For the first time, we can see detailed images revealing the birth of galaxies. It's an epic breakthrough for astronomers. This is the very first page in the family album. But these 15-billion-year-old pictures will guide us to even greater treasures, for they contain the blueprints of what the universe was to become. Astronomers will no longer be confined by the limit of what they can see. The microwave background offers the chance, for the first time ever, to explore beyond the known universe. As astronomers struggle to divine the shape and size of the cosmos, their explorations are limited. There's an edge to the known universe they can't see beyond. But it isn't a real edge. It's just a horizon. There's a much greater cosmos beyond our observable universe. Martin Rees is England's Astronomer Royal.
As we look further out into space, we look back in time. So there's a definite edge to what we can observe at the present time. But there's nothing special about that. It's rather like if you imagine being in the middle of an ocean on a ship. There's a horizon around you, which is, as it were, a circle on the ocean. But there's nothing special about that circle. It's just a limit to how far you can see. So it's important to distinguish the part of our universe that we can actually observe and the much vaster cosmos containing everything there is, which we can perhaps infer things about, but can never directly observe.
What excites astronomers is that beyond our small fragment of the universe, there is a greater cosmos waiting to be discovered.
We can only see to the edge of our own observable universe.
Our observable universe is like a bubble in the greater cosmos. We are always at the center of our own bubble, and we can only ever see as far as its edge. Someone trillions of light years away on another planet would be at the center of their own bubble. Unless these bubbles happen to overlap, we'd never be able to see each other. We would each be stuck in our own unique, observable universe. The edge of our observable universe is 15 billion light years away. If we could jump there instantaneously, it would be as if the veil of radiation had been magically lifted. We would see a new stretch of the universe with more galaxies, more stars, and more planets. We'd be at the center of a different observable universe that also stretches into the distance for 15 billion light years. And then what if we jumped again, and again, and again? It would be like walking up a hill, and at the top of every ridge, always seeing another horizon. Will there be a real end to our journey? A real edge to our universe? Or could we keep jumping like this forever?
There are really two options we see for the universe. One is that it is infinite in the sense that however far you go, there is no limit, there's always more beyond. The other possibility is that the universe is finite. Now, saying the universe is finite doesn't mean it has an edge. It may simply mean that it somehow closes up on itself, so that if you go on a long way in one direction, you do eventually come back and hit the back of your head.
When Christopher Columbus set sail from the Canary Islands to discover the New World, he knew he would travel in a straight line. If the world had been flat, he could have traveled forever across an infinite sea. But because the Earth is curved and closed round in a sphere, he could in fact have gone right round the finite world and eventually arrived back at the other end of Tenerife. The earliest explorers could not be sure whether the Earth was flat or curved. Today, cosmologists face the same dilemma about the shape of the universe. Jana Levin is a theoretical physicist at Cambridge University.
If the universe was flat and you were to head off in a rocket and travel in a straight line as you could, you would simply travel forever, never to be heard from again.
Alternatively, the universe could be closed into a cosmic curve, just as the Earth is closed into a sphere.
If you were to shoot into a rocket, travel in as straight a line as you could on that curved space, which would be a slightly curved line, but a straight line is allowed by the curvature of the space. You would find yourself, even though you never turned, never stopped, never reversed course, coming back to where you started.
If the universe is flat, you'd keep going forever. And if it is curved, you'd just go round in circles, no matter how long you traveled. The extraordinary possibility of curved space was first put forward by Albert Einstein almost a century ago. He told us that the key force that controls the shape of the universe is gravity. Gravity is the force which pulls objects together. It pulled an apple onto Newton's head. It pulls the Earth round the sun, keeps our feet on the ground. It also holds the universe together in whatever shape it is. With his observation of a falling apple, Isaac Newton first gave us the idea that gravity pulls things together, and that its strength is determined by mass. The greater the mass, the greater the attraction. But it was Einstein's insight, in his theory of relativity, to realize that on a cosmic scale, gravity can also cause space to curve.
What Einstein said is actually the Earth isn't exactly pulling on the apple at all. What's happening is the apple's following a natural curve in space that the Earth causes. So if you think of space as like a canopy and you were to throw a bowling ball on it, it would curve the shape of this canopy around the bowling ball. And things would naturally fall along these curves. And so things could fall into the Earth or orbit around the Earth, and they are following the natural bends in space. It's the same thing with light. It's not just rocks and matter that would do that, but also light does that.
We know from our own experience that light travels in straight lines. But suppose the gravitational force is so immense that the very fabric of space is curved. Then, the straight line which the light follows would itself be curved, and the light would appear to bend. The power of gravity to bend light is a graphic illustration of Einstein's celebrated theory. On a cosmic scale, the most extreme example of how gravity can distort space is a black hole.
A black hole is such an extreme situation that the space is curved so strongly that things don't just bend as they pass around it, they can make a full circuit. Light itself could orbit around a black hole, and it orbits unstably, meaning if it's slightly knocked, it's going to fall into the black hole, and then it can never escape. So the curve on space is such a deep nozzle that all the light gets attracted down to the black hole and cannot ever reverse its course and come off again. So what happens is the black hole becomes completely dark, hence the name. They can't emit light or reflect light.
The immense gravity of a galaxy can also bend light. If a galaxy were to pass between us and a more distant one, we would see a warped double image. Like a cosmic lens, light from the distant galaxy would be bent round the edge of the closer one. And in Chile, after just 1 month of scanning the skies for this unique effect, the giant mirrors of the VLT struck gold. On a dramatic night in November 1998, the VLT captured these stunning pictures. They clearly show arcs of light and multiple images of distant galaxies. This is a vital piece of evidence, proving that at least locally, space can be twisted out of shape by the massive unseen force of gravity. But what about the overall shape? Is the universe flat with a few wrinkles, or is it bent round into a huge cosmic curve? To resolve this, we need to know the total amount of gravity throughout the universe. In Australia, there's a man who's made it his mission to find out. By weighing the universe. At the Anglo-Australian Observatory in New South Wales, astronomer Brian Boyle is trying to weigh the universe. He's trying to work out if there is enough matter, and therefore enough gravity, to pull the universe into a curved, closed shape, or so little that it must be flat. He has already got an estimate of the amount of matter in our own galaxy, the Milky Way. If Brian Boyle can map and count all the other galaxies, he could work out the total mass of the universe.
What we do with the Galaxy Survey is we can look at how the galaxies are influenced by each other, and in terms of how they cluster together, how they group together in space, and from that we can measure the amount of mass that's there.
Brian Boyle and his team have developed a unique instrument called the 2-degree field, or 2DF, for his survey of the universe, the biggest ever undertaken. Most telescopes can only examine one light source at a time. But the 2DF instrument uses robotically positioned laser-guided lenses. Each tiny fiber optic cable separately carries the light from an entire galaxy and 2DF can analyze the light from 400 different galaxies at the same time.
The 2DF survey has allowed us to create an unprecedentedly large three-dimensional map of the universe. Imagine a locked room with a fantastical wallpaper pattern on the far side of the room. Before, astronomers were only able to peer through the keyhole at this wallpaper pattern, and so were unable to work out whether or not they were looking at a typical part of the wallpaper, indeed how large the pattern spread. Now with 2DF we've been able to unlock the door, and if not throw the door completely open, at least the door is now firmly ajar, so we can study this wonderful pattern, this wonderful structure and texture in the universe mapped out by galaxies.
And this is the result of the 2DF survey. A three-dimensional map of the universe, showing the true positions of over 200,000 galaxies, enabling Brian Boyle to work out the mass of the universe. Although it looks big, initial calculations show the universe to be much lighter than anybody expected. There's nowhere near enough matter in all these galaxies to pull the universe into a curved shape. But more alarmingly, there is only a fraction of the matter required to keep it flat. To make sense of his unexpected discovery, Brian Boyle has invoked two of the most mysterious forces in the universe: dark matter and dark energy.
Although the Galaxy survey has only found 1/3 of the mass required to make the universe flat, we now believe that the remaining 2/3 of the matter energy in the universe is contained in this so-called dark energy.
Astronomers have long speculated that in addition to the familiar matter of stars and planets, there is a vast proportion of the universe that is invisible, made up of dark matter and dark energy. But where's the proof? These forces are just theories. Until now. In one of the most remarkable discoveries of recent years, the evidence has been found in the microwave background radiation. This radiation, that has traveled through space since the beginning of time, has confirmed the existence of these invisible cosmic forces. When it reaches Earth, the size of the radiation hotspots tells us about the shape of the space it has traveled through. What they confirm is that the universe is far from being curved.
They can tell us certainly about the shape of the universe. And what we're learning so far is that space is pretty flat, pretty close to being flat.
Because the radiation hotspots arrive at the VSA undistorted by their long trek, they prove that the universe must be flat. If the universe was curved, the spots would appear much larger, magnified by the curves in space. In proving that the universe is flat, the microwave background has also confirmed that astronomers were right to assume the existence of dark energy and dark matter. The stars, the planets, the moon, everything we see is just a small fraction of the total cosmic mass. Most of the universe is invisible. Although we believe the universe is flat, we know it is far from calm. Space is stretching. We've known since the 1920s from the pioneering work of the American astronomer Edwin Hubble that the universe is expanding. It started at the moment of creation, in the Big Bang. Everything in the universe was created from a cosmic fireball smaller than an atom. After it was thrust apart by the violent momentum of the Big Bang, we're now confident that the universe has been expanding continuously for 15 billion years. Paul Davies is a British cosmologist working in Sydney.
Well, the universe is certainly expanding at the moment. There's no doubt about that. We see the other galaxies rushing away from us and from each other.
But the big question is whether the expansion will continue forever.
The situation's a little bit like throwing a ball up in the air. You throw it up and it comes down again. But if you could throw it hard enough, it would leave the Earth entirely. And we don't know whether the Big Bang was powerful enough to, so to speak, propel all the bits apart so that they would escape their own gravitation and go on expanding forever.
Or will the universe stop growing at some point and start shrinking? If there's enough matter and enough gravity, the universe could collapse in on itself in a reverse of the Big Bang.
It's vitally important to know how much stuff there is in the universe. And one of the breakthrough results of the Galaxy Survey has been to find that essentially there isn't enough mass in the universe to stop the universe from continuing to expand on to infinity.
It seems our fate is sealed. The universe will continue to expand forever. But how fast? As well as weighing the universe, Brian Boyle's Galaxy Survey can also tell us how quickly it's growing. His technique reveals how fast the galaxies are moving. It's like a speed camera that records which direction a car is traveling and how fast. So far, astronomers have discovered that galaxies are not only rushing apart from each other, they are gathering speed. It seems that 4 billion years ago, the universe changed up a gear, and ever since has been expanding faster and faster. But what is the force driving this cosmic acceleration?
Now, if it's true that the rate of expansion is picking up, that suggests that there's something like an anti-gravity force, something opposing the normal force of gravitation, the pulling force, something pushing the galaxies apart faster and faster.
This anti-gravity force is dark energy. Astronomers now believe the universe must be buzzing with this invisible energy. Space, it seems, is far from empty. We just can't see what's out there. The unseen forces of the universe, gravity and dark energy, are locked in the ultimate battle. At stake is the destiny of the universe.
You have two competing forces to the expansion of the universe. You have all the matter that's contained in the universe, the galaxies, the quasars and the stars. They're, if you like, the brake in the car. They're trying to slow down the rate of expansion by their gravity. The other force, the so-called dark energy, is the accelerator pedal in the universe. This is the energy that's trying to accelerate the universe apart. Well, in this battle of these two forces, it's the dark energy that has won, because we now know that the universe is accelerating and will continue to accelerate to an infinite size at the end of time.
Inside each galaxy, gravity is strong enough to keep all the stars clumped together. But in the void between galaxies, dark energy is too strong and the fabric of space is stretching.
If we imagine leaping forward into the future by trillions of years, a truly enormous length of time, there would be largely emptiness. The other galaxies or supergalaxies would completely lose touch with each other. It would be impossible for any light to travel from one to the other. So it would be a very lonely place in the far future of the universe.
The universe is locked into a desolate and lonely fate. Dark energy will defeat gravity and succeed in stretching the universe into oblivion. All our ideas about the cosmos, what shape it is and what it's made of, will be thrown more sharply into focus when the MAP probe heads off into space. MAP will provide the first ever complete detailed survey of the microwave background radiation. By looking back to a time just after the Big Bang, when the universe was 1,000 times smaller than it is today, the MAP probe can look at the universe in its totality. It will beam back a detailed image of the entire infant universe and put cosmologists' ideas to the test.
It's a very exciting time in cosmology. We seem to be converging on the standard model where the universe is flat and it's made up mostly of this dark energy and there's dark matter. And it seems to fit all the observations we have at the moment. On the other hand, this model we have requires dark energy that we've never seen, dark matter, which also we've never seen, and the atoms that we know about are supposedly making up only 5% of the universe. And it's, of course, a tremendous act of hubris to think that our ideas about the universe are so likely to be correct that when this probe goes up, we will be able to very accurately predict what the universe looked like 500,000 years after the Big Bang.
When the results from the MAP probe are beamed back to Earth, they could reveal things about our universe which are beyond our wildest imagination.
I think that's what makes this so exciting, is that in a few months, when we really start having maps of the whole sky, we'll have this image of what the whole universe looked like at this very early moment, and test these ideas and see if they are indeed right.
The microwave background can take us almost all the way back to the beginning of the universe, but not to the actual instant of birth. This moment remains tantalizingly out of reach. We may never discover exactly how and why the Big Bang happened.
I suppose the ultimate problem of cosmology is, how did the universe come to exist in the first place? Was it a natural process, or was it something like a miracle? Well, scientists would like to believe it's a natural process. The problem is about a natural process, if it can happen once, it can happen again. Indeed, it can happen an infinite number of times. And so this has led to the speculation that there isn't just one universe, but maybe an infinity of them. That doesn't mean that there are other universes out there or out there. It means that they would, in some sense, be in their own space and time.
It seems bewildering, but our universe could be just one of an infinite number, just one speck in a never-ending multiverse.
The multiverse itself might have no beginning or end, but any given region of space and time could originate in a Big Bang and have a life cycle, a beginning, a middle, and an end. There could be big universes like ours and baby universes, perhaps momentarily clinging to them and then disconnecting, expanding up in their own way.
If there is a multiverse, then there could be an entire array of extreme universes. Ours is a delicate balance between matter and energy, essential for the evolution of planets and life. But others could exist which are far more hostile. Some made purely of matter, for instance, with no energy. Or there could be a universe which is just energy with no matter at all. Each universe would have started with its own Big Bang, each with its own laws of physics.
If there are many Big Bangs, then this raises another interesting question, which is, how similar are they to the one that gave rise to our universe? Are they all replicas of our universe, or could they indeed be different? They might, for instance, expand too fast, or have very short lifetimes, or for various reasons they might not allow the complex evolution to occur within them that has led to us.
If there is a multiverse, then anything that can happen will happen somewhere in a parallel universe.
Every combination of circumstances that happened, for example, on Earth would eventually happen somewhere else. So there would be duplicate Paul Davises, duplicate Elvis Presleys. But for every other Elvis Presley out there somewhere in the distant part of the cosmos, there would be squillions of near misses, near Elvises, all over the place.
However intriguing a thought it is that in a parallel universe Elvis Presley is alive and well and playing the Sydney Rock and Roll House, it's something we could never prove. We could never visit another universe. We'd cease to exist as soon as we left our own. This is a dramatic time in cosmology, as we put our theories on the nature of space and time to the test. It's 3:46 p.m. on the 30th of June, 2001. The MAP probe is moments from blastoff.
Mostly I'm excited. I have this real sense of this assignment we've been working towards for 6 years, and it always seemed very distant. And now it's suddenly real. And it's going to happen.
10, 9,
8, 7,
6,
5, 4, 3, 2, 1.
Ignition is looking good. Load release kick rate is in. Vehicle is responding. Vehicle's working its way through the liftoff transient. System's looking good. Approaching Mach 1. Usual attitude disturbances through the thick atmosphere and the Mach buffeting. We are now supersonic. Ignited the air start motors and jettisoned the ground start.
That's beautiful.
In the last few years, we've mapped out the broad outline of cosmic evolution. We understand the main ingredients of our universe. It's made up of atoms, dark matter, and some mysterious dark energy which drives the cosmic acceleration. But there are many things, of course, which we don't understand. Indeed, it's the nature of science that the more advances you make, the longer the frontier gets, and the more new questions swim into focus, as it were.
3 months after the launch, the MAP probe reached its stable orbit 1 million miles from Earth. It is now beaming data to David Spergel about the formation of the universe. Over the next few years, our view of the cosmos may be changed entirely. The ingenuity of astronomers is laying bare the wonders of the universe. Their quest has taken them closer and closer to the edge of the universe. Today, their final frontier lies at the instant our universe was born. But tomorrow, even that frontier may be conquered.